Dear friends, good morning and welcome you all for today's class. Today we are going to discuss about nozzles and diffusers. Nozzles are very important, you can say component of the steam turbine power plant, and there are so many applications of nozzles and diffusers. You can see in jet engine, particularly in steam turbines, and you have seen in jet engine where and there is a nozzle through which very high speed exhaust gases come out and engine produces very high power thrust, very high power thrust, and this thrust is used for the propelling of the aeroplane and in space ship and rockets everywhere we use these nozzles are used. These are convergent and combination of convergent divergent nozzles. These are very effective in producing very supersonic velocity and even hypersonic velocity in rockets. So today this is very important. And in steam turbine and even in gas turbines, the nozzles are used. And so first we discuss what is a nozzle, and then we study flow energy equation for nozzle and mass flow from the nozzle and coefficient of discharge, nozzle efficiency, and we develop. This is very important topic from competition point of view, GATE examination, Indian Engineering Service examination, and this topic is a must. And I no competition you can see that. Question from this topic will not appear. So this is a very interesting topic, and in Indian Engineering Service examination you will find one full question, whether it is in mains examination, and in prelim examination you will find 3 to 4 questions from this topic overall. So that's why it's very important. So starting from basic, what is a nozzle? So nozzle is a device which provide a passage, flow steam or gas and pressure energy and thermal heat energy of the steam or gas is used to convert into the kinetic energy. So nozzle, if it is a convergent divergent nozzle, then pressure and thermal pressure and heat energy is converted into kinetic energy. If it is a diffuser, then kinetic energy is converted into pressure energy. So whatever function, maybe we use different types of nozzles and diffusers. So here we will start under so many applications. You can see main application, I already discussed that it is used for in steam turbine power plant when steam from the boiler will enter into the turbine through different nozzles, fixed nozzles. The nozzles provide either pressure, increase of pressure or increase of velocity. So you will see in steam turbine series of moving blades and fixed blades are there, and fixed blades are fixed blades acts as a nozzle, and so many applications in heat engine and in jet engine and rocket and steam turbine. So starting from the steady flow energy equation. So steady flow energy equation. So this is a this is a nozzle, and we see this is a nozzle. This is a inlet condition, and this one is a outlet condition. So first we develop, just apply first law of thermodynamic law and conservation of energy. We develop what is a exit velocity, because mainly when steam enters or gas enter into the nozzle, is entry side and exit side, exit and entry side. Here condition V1 is a specific volume, C1 is a velocity, H1 is enthalpy, and U1 is enthalpy. These are values per unit mass. These are values per unit mass, and Z1 is suppose this is a datum. This is a datum. So we will take Z1. Let Q1 is a heat entering, and W is a work done. Also we will take, and Q1 is a heat entering from Q1 is a heat entering. Q1 is a heat and Q is a heat entering. So exit condition will be V2 and C2 and H2 and U2 and Z2. So this is these are inlet. V1 means C volume meter cube per kg. V is basic volume. V stand for basic volume, and C1 velocity of steam meter per second will be a meter cube per kg, and H1 enthalpy at entry. Enthalpy means total heat, kilojoule per kg, and U1 internal energy kilojoule per kg. Z1 is a datum. Z1 is a datum height of the entry from the datum. So Z1 and Z2, these are two positions. This is a Z2, but these are same. You can see from datum Z1 is equal to Z2. Z1 equal to Z2. So these are entry and inlet conditions. We have to write a free flow energy equation for this configuration. So let us minimize this one. Writing energy balance equation. Writing energy balance equation for nozzle. So you know that at entry and incoming energy equal to outgoing energy. So H1, uh, P1 we have not defined P1 and P2. These are pressure. P1 and P2, these are pressure. Pressure at inlet kilopascal, pressure at outlet in kilopascal, yeah, or pascal you can define. So writing energy balance equation at entry and in inlet, because there is free flow energy equation, no accumulation is there inside the nozzle, and generally we take nozzle is in body surrounding of nozzle surface is insulated one, so there is no any heat dissipation from the nozzle coming from outside or from inside. So surrounding to inside, and nozzle is not device which perform any work. So these terms will become zero later. So including all parameters in energy balance equation. So P1 V1 P1 V1 plus internal energy U1 plus C1 square by 2 and plus Z1 G equal to P2 V2 plus U2 plus C2 square by 2 plus Z2 G. These are plus we can say here we have Q equal to plus W. W is work done. We here we have to simplify things, because we know that in case there is no any heat transfer take place, because it is surrounding is nozzle surface is fully insulated, so Q equal to 0, and nozzle is a not device which perform a new work. So only it provide a passage for flow of steam through. This is a passage through which steam will flow. So no work is done by the nozzle. So W will also become 0. Just for making you understanding how many parameters are possible to include to write energy balance equation. So you know that this term P1 V1 plus U1 and P2 V2 plus U2, it is a enthalpy, it is a H1 and it is a H2. These are enthalpy terms. So H1 plus C1 square by 2 plus Z1G equal to H2 plus C2 square by 2 plus J2G. And here also we can see that Z1 equal to Z2, Z1 equal to Z2, because inlet condition and outlet condition are at same height from the datum, and this one is a datum. So we can put Z1, this term becomes 0, this term will be replaced 0. So simplified equation you will get H1 plus C1 square by 2 equal to H2 plus C2 square by 2. Here we have to find out C2 value. But one thing just I want to remind you that in this equation, H1 is in kilojoule per kg and H2 is also in kilojoule per kg, and C1 is in meter per second. Well, after we have taken meter per second, and mass is in kg, we have taken 1 kg. So to make it uniform, you have to multiply by divide it by 1000 to convert it into this term, because this is a kinetic energy term. So we have to multiply it by 1000 to homogenize the equation, because H1 is in kilojoule and C1 square by 2 in joule. So dividing by 1000 you will get kilojoule, here again kilojoule. So now balance this equation, C2 square minus C1 square upon 2000 equal to H1 minus H2, H1 minus H2, and C2 square minus C1 square equal to 2000 into H1 minus H2. So this is equation for finding, but in case that Inlet velocity in nozzle is almost negligible. Most of the cases you will find inlet velocity of nozzle C1 is very small compared to C2. C1 can be equated to 0. So now further equation will simplified. This equation will further simplified. C2 square equal to 2000 H1 minus H2, and then C2 equal to under root 2000 H1 minus H2, and you should take under root of this 2000. It is equal to 44.72 H1 minus H2. This is the equation for nozzle exit velocity, and this equation you can take if initial, even if it is not initial term is not, C1 is not negligible. By making it C1 equal to 0, you will find very small insignificant difference in your answer. So C2 you can use this equation H1 minus H2. This is for the nozzle exit velocity when steam is a working fluid. When steam is a working fluid, same equation you can modify it for the gas nozzle. Gas nozzle also you can simplify. So only small modification is required. For gas nozzle you have to reduce H1 H2 in terms of, because you know H equal to CPT at constant H equal to CPT. Putting value of then C2 can for gas nozzle. For gas nozzle you can put CP. Taking for gas nozzle, so C2 equal to 44.72. C2 equal to 44.72 into Cp H T1 minus T2. You can take 44.72. You can take T1 common. Cp T1 1 minus T2 by T1. So in terms of pressure difference, you can simplify this equation. If there is a gas nozzle, simply this equation you can use. 44.72 values will be given, Cp will be given, T1 minus T2 is our temperature difference, and you can simplify T1 T2 in terms of pressure difference. Whatever data is given, whatever values are given, you have to modify this equation. But this is the most important equation, and so many times you have to calculate exit velocity by using this equation. Now let us see what is nozzle efficiency. This we have considered that there is no any frictional losses, no any change in entropy. This we have considered that flow is isentropic, but actually in spite of nozzle surface is very smooth, some percentage of the frictional losses are always there whatsoever surface smoothness you can maintain. So how we can calculate nozzle efficiency? Let us see nozzle efficiency. Nozzle efficiency. This term is for real flow of the nozzle, because we know that some percentage losses of heat energy in terms of overcoming frictional resistance of the surface will always take place. So if we consider this point, then exit velocity will be less than actual velocity. Exit velocity of the nozzle will be less than actual velocity. So let us define by using enthalpy entropy diagram. Drawing a enthalpy and entropy diagram H and S, taking pressure lines here, pressure P1 and here is pressure P2. Suppose it is a starting point. So this is a starting point. This one is a starting point, and this is isentropic expansion. Suppose this one is earlier it was isentropic expansion. This is a actual ideal isentropic expansion in which entropy remains constant. This is entropy. So entropy remains constant during ideal isentropic flow, but this is not the case. So here you can see enthalpy is H1, and here you see enthalpy is H2 after expansion. These are two terms you see, state 1 and state 2, 1 1 and 2 2, and here you can see velocity is C1 and here velocity is C2, and this is a insulation. You see that in isentropic flow, enthalpy, there is no any change of entropy, but in actually what is occurring due to frictional resistance, flow expansion will be like this. This is a H2 dash, H2 dash, H2 dash. So lesser amount is now due to frictional losses, entropy will increase, and so you can see this is a change of entropy. This is a change of entropy delta S due to frictional resistance. So in this case, actual velocity you will find is now this C2 square, C2 dash minus C1 square by 2. Change in kinetic energy. Actual kinetic energy was this, you see C2 square minus C1 square by 2. This is the actual change of kinetic energy. But ideal case of ideal change in kinetic energy, and if it is actual change in kinetic energy, because now lesser amount of heat drop takes place. That is useful for converting heat energy into kinetic energy. Lesser amount of heat drop. Now only H1 minus H2 dash is available for the change of kinetic energy. Earlier it was H1 minus H2. This is a more heat energy available to convert kinetic energy. So now you can see C2 will be less. So how you define, how we can define nozzle efficiency? How we can define nozzle efficiency? Nozzle efficiency can be defined. Nozzle efficiency now here. Let us further reduce size. So nozzle efficiency can be defined NN. Nozzle efficiency can be defined as actual heat drop. Actual heat drop upon isentropic heat drop. Isentropic heat drop. That is equal to H1 minus H2 dash upon H1 minus H2. This is H1 minus H2 dash upon H1 because lesser amount now heat is available. So actual heat drop upon isentropic heat drop. This can be written as in terms of the actual kinetic energy gain upon isentropic kinetic energy gain. So C2 square, C2 dash square minus C1 square upon C2 square minus C1 square. This is the nozzle efficiency N equal to C2 dash square minus C1 square upon C2 square minus C1 square. Again, we can further simplify because we know that initial velocity C1 is very less than C2. So C1 can be neglected. C1 can be neglected. So equation will be reduced in terms of NN nozzle efficiency equal to C2 dash square upon C1 dash square, or you can say C2 dash upon C1. You can also define as K1 coefficient of nozzle efficiency, coefficient of nozzle C2 dash square upon C1 square, or C2 dash square Kn. This term is known as a nozzle. This one is nozzle efficiency. So you can see that in convergent divergent nozzle, in convergent nozzle, the flow is more secure and more lesser amount of frictional losses you will see. But in divergent part, there is a divergent part means opening is diverging, and so flow there is a greater chances that flow may C2 dash square upon C1 square Kn square. This is known as the nozzle coefficient. And so how we design nozzle? This is a only convergent nozzle we have seen. So here you can see because it is converging, so chances of flow separation are almost nil because it is converging. But in diverging, when diameter is continuously increasing of the flow passage, then chances of separation are more. And if there is abrupt expansion takes place, then there is chances of flow will separate from the surface. So in that case, more frictional loss will be there. So we must keep very careful design of the convergent divergent part of nozzle so that flow separation will not occur. So how we decide the diameter of the diverging part means what will be the length of the nozzle in divergent part. So that is we have to decide because angle according to practical constraints and practical applications we have seen that angle should be between 6 degree to 12 degree. Divergent angle should not be more than 6 degrees, but maximum allowable angle is not more than 20 degree of the divergent part. So let us see how we calculate length of the divergent part of the nozzle so that frictional losses can be minimized and efficiency of nozzle can be increased, because efficiency of nozzle is very important significance in increasing, very important and significant factor in increasing thermal performance of the steam power plant. So let us see how we decide nozzle diameter. This is you can say throat. This is a throat and this is a part of the exit and this is a inlet 1 and 2 and 3. So let us take a, now see what is the total angle. This is a draw tangent on this one and draw tangent on this one. So this angle is known as a psi. So this angle becomes psi by 2 and this one also becomes psi by 2. And length, this one is length of the divergent part is let L and exit diameter is let, it is a d exit, and this one is a d throat diameter. This is a throat diameter, d throat diameter. So now we see that what is this value? This is equal to, how much this is equal to? D exit minus D thought minus by 2. This is equal to, and this is also, this value equal to, you see, D thought, D exit minus D thought upon 2. Because if it is whole diameter and this you reduce, you will get two parts. D exit minus D diameter means two parts, remaining two parts. So one part, this one is equal to D exit diameter of the exit of the nozzle minus throat diameter upon 2. So this will be equal to D exit minus D third upon 2 and this one is L. So tan psi by 2. Tan psi by 2 equal to D exit minus D thought by 2 upon L. So this is one. So from this equation you can find the length of the convert divergent part equal to D exit minus D thought upon 2 tan psi by 2. 2 tan psi by 2. So this is a very important equation in design of nozzle. Most of the cases you can be asked to find out the length of the divergent part of the nozzle. So mostly in steam turbine or jet engines or jet planes and rockets, convergent divergent nozzles are used. So this is very important. And next we will discuss about flow maximum discharge nozzle. One thing still remaining to define, what is a coefficient of discharge. Coefficient of discharge, because we know that coefficient of discharge, again we know that due to frictional losses, actual discharge is less than isentropic discharge. Due to frictional losses occurring in convergent divergent part, actual discharge is less than isentropic discharge. So this ratio, the coefficient of discharge, you can define CD equal to define as actual discharge upon isentropic discharge. So this is also because this value is always less than, never can be equal to 1, because actual discharge is always less than isentropic discharge. So this is all about for initial discussion. And next lecture we will discuss about what is a maximum condition of maximum discharge, what is a discharge, and also introduce you about momentum equation for nozzle. We will not derive this equation, but we will introduce how we use momentum equation, because this one is very lengthy. And only thing that you have to remember equation of the momentum equation. So next class we will discuss mass condition of maximum discharge and choked flow conditions, and in what is the velocity at thought during choked flow conditions, All these things we will discuss in next lecture. Thank you very much for watching my video. Please